in physics. Everyone has studied physics if you have in an engineering background in your first years, and your schoolings also. The term lattice was used commonly with respect to atomic crystal size, like a body center cubic, or face center cubic, or cubic lattice. People have used this term a lot of times, right? And the same here in additive manufacturing also, the same kind of lattice terminology is used, which has a three dimensional structure. So it has a shape variation in x, y, and z axis. And if the lattice is repetitive along x, y, and z direction in a repetitive manner, then it becomes a lattice structure. So it is a periodic or aperiodic networks. Periodic means that the same unit cell is repeated along x, y, and z direction. Aperiodic means that there will be a variation in the static of the lattice. If we are using this functionally graded lattice structures, then the structure will be varying along x, y, and z direction. Or we can have this kind of customized lattice structures where a particular region will be of one lattice structure and another region will be of another different lattice structure. And those things are called as aperiodic lattice structures. So what is the use of that is to achieve lightweight and high performance parts. So we need to have lightweight parts, or we need to have some better OSI integration. In such cases, these lattice structures are useful. And these lattice structures are not only restricted to a particular domain. We can also use it for mechanical engineering application for weight reduction, and thermal engineering application for better heat dissipation, and for biological properties like for OSI integration, and for tissue engineering applications. For such kind of applications, it can be useful. So uh, this can be applicable for aerospace, biomedical, and industrial sectors. That was the just a minute. There was a beep. I just yeah. Sorry for the interruption. Yeah, thank you. Yeah. So here, these lattice structures are applicable in mechanical, thermal, biomedical, and various domains. And you can see this is a 3D printed. All the lattice structures are printed with metal additive manufacturing, because the metal additive manufacturing powder cost is very high. And this kind of lattice structures, if we need to have lightweighting, we can, and for a reduced cost, we can use this kind of structures over here. And we can also use it for weight reduction. This is actually an aerospace bracket. If this particular space, we need to reduce the material, but we need to have some connectivity between the elements. For such application, we can implement this kind of lattice structures for weight reduction applications. And you can have this kind of satellite part, which is printed with the titanium meta material. This kind of materials will reduce the weight of the powder which is being used, as well as it can increase the strength with reduced cost. So such kind of application we can make use of it. And 3D printed ceramic, you can see, which is printed with the lattice structures, which is stronger than the diamond lattice original material, which was proven. And you can see lattice structures which was incorporated in the helmet. And this is actually an automobile part, which is a bearing, which is we can able to generate the lattice using this technology called generative design or a topology optimization. And I will show you in my slides what are the softwares available, where you can make use of the commercial software or open source software to make this kind of lattice structure for starting your research in. And this kind of lattice structures have been classified into stochastic and non-stochastic. And 3D structures are truss-based, surface-based, Voronoi-based and topology optimization. What is a truss-based? This truss is commonly used in civil engineering, where you can have this kind of elements in the form of octet, face center cubic or body center cubic. You know the what is face center cubic, right? If you have a unit cell, right? If we have a unit cell like this, and if you have this kind of atoms present in all the faces, then it is called as a face center cubic, right? And body center cubic, everything you know, right? And same kind of, if we have some hollow space in those kind of in those regions, then it is called face center cubic, and it is a body center cubic. Like we can have a variation with respect to the uh, future which we are keeping behind the physics of that model. And we have this kind of a surface-based model, uh, which is a TPMS, which is type-right periodic minimal surfaces. I will show you this TPMS model in the upcoming slides. Here, this TPMS structures has a surface element instead of a solid element. We can have this kind of surface element to create these lattice structures, and we can have this Voronoi based. This is Voronoi tessellation is irregular shaped structures based on the cell seeding. We can able to create this tessellation, especially for creating this STL files, and same we can also implement it for making these lattice structures also. And topology optimization is based on this weight constraints or the load, or if you provide a certain constraint to the for reducing the weight, we can create a topologically optimized geometries. Such geometries also we can consider it as an unit cell, and we can able to create the lattice structures over there. And these are 3D structures. And if we have a 2D structures, which is a wall based, if you have XY, and in that XY, if we create a lattice structure, if it is repeating along XY in Z direction, that is 2D structures. And we have this stochastic lattice structures, which is open cell and closed cell form. Open cell form means like the form, as a irregular shaped structure. And those irregular shaped structures, if we have a surface which is not closed, or if we have um, the, entire surface, like if you are having um, a a box, and the box has a lattice structures. If we have if you visibly see the lattice structure, then it is called as open cell form. And if we have a surface closing that entire form, and that is the presence of lattice inside that, then it is called as a closed cell form lattice structures, and it is a stochastic form. And some of the advantages of this lattice structures are this BCC, which I talked about right now, which is the body center cubic. The atoms are present along the corners and at the center of the unit cell. So here also the studs are connecting along the corners and at the center. And so this is BCC structure. And I told you about this octet truss, which is a kind of lattice structure, which is connecting the edges of the unit cell and to the center, and everything will be connected with the help of connecting points through a single, not you can say single connecting elements. So we can have this kind of lattice structures for higher stiffness. And if you need to have more compliance and good manufacturability, because if you are printing with the help of metal additive manufacturing, you need to have this the kind of thermal gradient should be better. So this kind of lattice structures provide a better thermal gradient, and here there will be a possibility of a distortion more. But you can, if you print it, we can able to have this kind of higher stiffness in the printed parts. So here you can see in this particular element, which is a beam, which is thermally studied, and they found this topology optimization, which is not is mechanically studied by applying the force. And for that application, we need to have minimum load which is starting here and more load which is concentrating at the center. For such application, if we need to have a higher load carrying capacity, we can implement this kind of higher stiffness lattice structures. We can use this octet stress. We can implement the octet stress in this particular regions, and then we can also have this kind of BCC lattice structures in this particular region. So this how we can implement functionally graded lattice structures in this particular element. You can see this multi-lattice design here. Multi-lattice means there will be two different lattice which is present here. Just here. So here you can see the stud size which is minimum, or the BCC element which is present here. And here you can see a different lattice, which is octet, which is present here, according to the load bearing requirements. So such kind of application, we can have a combination of higher load carrying capacity and stiffness and material, less material consumption constraint also. So these are the current area of research where the knowledge of um, analysis we people have been working on for like over a period of time to optimize the weight, and this additive manufacturing combined together to make some innovative products to the market. And then we can have a design freedom because the additive manufacturing, the main concept is that it's a design flexibility. If you know the concept of a design for additive manufacturing, we can print whatever we can by studying certain constraints. Um, so here, if we have a design freedom, we can create a complex lattice structures that are impossible to manufacture with the traditional methods, which can be printed with the help of additive manufacturing for end-use application. And we can have this kind of customizable mechanical properties by adjusting the unit cell size, type, density. We can able to create a stiffness strength and energy absorption capabilities into our lattice structures by studying the kind of lattice unit cells properties. We can able to implement for which lattice has more stiffness, which lattice can able to absorb more energy, especially for impact applications. This kind of lattice structure supports in reducing the weight as well as increasing the amount of energy absorption of the capabilities. And here this improved heat transfer. So here for thermal application, you can see when the surface area of a material or any surface area is more, then there will be a thermal gradient. You can able to um, what you can say is as the convective surfaces is more, you can transfer the more heat from the material to the external surfaces. The heat transfer capability will be more. So, such kind of lattice structure, by default, it has more surface area compared to a solid material. So, and it helps to provide a better thermal management for a heat exchanger application and for electronic cooling due to increased surface area. So people have been studying with the help of lattice structures for improving the thermal gradient or improving the heat transfer capacity for cooling fins applications, especially with respect to electronics. And you can have this biomimicry. Biomimicry is an innovative field in a medical application where we can able to create a lattice structure mimicking the surface properties and the properties of the bone. You can, because the bone is not completely solid, it has a porous structure which is present inside. We can also mimic those kind of features in the implants which you are creating. And we can also study for osseointegration, because those lattice structures not only reduce the weight or make the properties, it also assists for improving the bone growth. Then we can have a better osseous integration for orthopedic and dental implants. Orthopedic means the implants which is related to the bones of thighs, or the femoral processes and hip implants, or whatever the connecting places people have been now the tissue which is having a connection with the bones, and if you are replacing the bones in the with respect to the fractured bone or with respect to the connecting bone joints, those things are called as orthopedics. And dental, which is related to the face, like jaw, and then oral maxillofacial, whatever the structures which is present inside our face, like a bone structures, those things are related to dental. So for those application, you can use this. And lattices are also not only reduce the material usage, it also reduce the cost, and it create an environmental impact, because um, material cost almost now constitutes 50% of the material, whatever the product which are being used as an engineering product which are used. So if we have option to reduce the material which have been used in the product which are manufacturing, then obviously it will have a good sustainable impact over a period of time. We can consume the material less and we can use it effectively, not all the available materials in them. And you can have this kind of applications in aerospace, like the structures. It's like a clamp. Um, it's a G engine bracket, uh, where you can also implement this kind of lattice structures for heavy reduction applications, using this topology optimization. And this is actually a kind of uh, thermal barrier blades, like it's like a fin, where we can implement the lattice structures inside for effective heat transfer applications. And also we can have this kind of lattice structures where world-renowned space organization, which is NASA. They have been working on with this metal additive manufacturing technology to create this kind of brackets for satellite mountings in their applications. Apart from that, we can also study this for possible applications. Right now, the metal additive manufacturing is costly, because most of the patents are with OEM companies, or the patent. Once the patent expired, like how material extrusion, the patent, uh, like the technology, when the patent got expired, for the last 10 years, it is very cost effective. Like that, once the patent got expired, and if we even open those things, it comes into the market, and we can have this cost reduction in those parts which can be printed with the metal additive manufacturing. For that, we can also have some knowledge, to pioneer ourselves in those kind of research, uh, and make ourselves um, better in those application, in those environment. Then we need to have some knowledge in that. And people have been currently started research in how we can able to use this kind of lattice structures for bicycle. Bicycle. There'll be a rod which is present there. If we can have this kind of lattice structure, obviously it can reduce the weight, as well as it can have more load-bearing applications. So this was one of the interesting application which I'm sharing in the automobile. Like that, there are plenty of application people have been working on for automobile things. Apart from that, this lattice structures are also used in fashion industry. So we can see the shoes. People have been this kind of shoes, but under the we can see this shoe insole or the shoe bottom are completely made with the lattice structures. So this have a more cushion effect as well as a reduced weight, providing better comfort for the athletes or the people who have been wearing this kind of things. And for the fashion industry, this kind of knitted structures, we can have this kind of lattice structures. Um, so people have been exploring how additive manufacturing supports in creating these lattice structures, especially in Tokyo Olympics, US. Um, uh, they US athletes have used this kind of shoe insoles with the lattice structures, and it was proven compared to previous Olympics, the athletes have performed well. So you can also think of such kind of applications and research into it. And apart from that, we can also have this kind of lattices in architecture applications where you can have a large structure which needs to be printed, and we can have this kind of lattice structures so that the weight of the structure will be reduced and we can get more area. These are some of the structures which you can see uh, uh, a huge robot which is whose size is bigger than the size of the human, uh, 6 feet. So it is printing a structure over of 10 feet or something like that here. So you can also have such kind of uh, thinking people have been working on with some innovative concepts for various applications. Apart from that, the main application of lattice structures in healthcare is this implants. So we can have a range of implants like orthopedic implants for better osseointegration and reducing the implant stiffness mismatch. Like if there is a mismatch between if you print a part completely solid with more stiffness or reduce the stiffness. If it have more stiffness, then the more the implant will carry and the bone, and then the adjacent bones may tend to failure more. Or if we have a reduced size of the implant, we can't able to fix it properly. So such kind of things we can able to have a trade-off between the size of the implant and the density of the implant with the help of this applications. Thus minimizing this stress shielding effect. And apart from that, we can also have this kind of cranial and maxillofacial implants. Cranial means the implants which is related to the skull. And the maxillofacial means the implants which is related to the face. What are the bones is presented on the face, that is called as a maxillofacial implants. So for skull reconstruction application and bone scaffolds for regeneration application. So you can have this kind of scaffolds. I already told you it's a unit cell which assists in bone growth as well as mimicking the bones which is present in our body. Apart from that, we can also have this kind of spinal implants for our backbone. So this backbone, the center of the backbone, we can have a kind of a um, uh, vertebrae. That vertebrae also, that over a period of time, people are going for surgery for replacement or something by placing an implant over there. So here, if we can also print the implants with the help of material like a titanium or stainless steel, we can implement those things as a replacement of the bones which is present there. And then we can have this kind of dental implants for fixing the whatever the teeth below the teeth, that is a jaw. And so those jaws we can also have this kind of implants uh, for fixing the dental bones which got failed over a period of time because of cancer or because of uh, age restrictions. So for that, this kind of implants with the lattice structures are very much useful. I also show you some applications which we have tried in our lab with the help of this with the help of these implants. So already I told you this is in the first slide. This is a unit cell. Um, it has a lattice points, and if we have a generation of general definition of unit cell, which is repeating along a three-dimension x, y, and z axis. And you can see the simple cubic, which has a bones at the which has atoms at the corners of the unit cell, and body centered, which has a unit repeated along x, y, and z direction. Then it is called as an array. Those arrays are called as an lattice structures. And we can have this kind of unit cell, which is connected with the help of various studs. And this is a body center cubic BCC lattice cell, lattice unit cell. And if we have this lattice unit cell repeated along x, y, and z direction, then it is called as a PCC lattice structures. And we can have this FCC lattice structure, which has a unit cell along corners and at the center of each faces. So same here also the lattice cell which are printed as a at terms at the corners and which is connected with the help of various studs at the center. And if we connect it, then it becomes a three-dimensional structures. So here I told you the based and surface based and stochastic and hybrid lattice. What is the difference between the main four differences of this unit cell is that the studs are connected like the BCC or FCC. The studs are connected along X and Y and Z direction. So it's composed of beams or rods are connected at rods. But if you have this kind of surface based, you can have this kind of complex geometries like gyroids, diamonds, Sheward's P. So these are called as a smooth surfaces. So instead of strong transition, you can have this kind of smooth transition. So for effective load transfer application and reduce corners, sharp joints, especially for biomedical implants or fluid flow application. This TPMS structures people have been working on, and this is actually a stochastic lattice structures, which is a random or the Voronoi or foam based, which is mimicking the natural porous materials like bone, foam, just good for energy absorption or biological scaffolds. So this stochastic lattice structures are not regular lattice structures as like the previous one. So it has an irregular unit cells. The unit cell size and dimensions are not same along x, y, and z direction. And if you have this hybrid lattice structures, which is a combination of one or two unit cells, you can see this stud based and then surface based combined, and you can make a combination of strength and flexibility and for tailored mechanical properties. This kind of lattice cells people have been working on. And you can see these lattice structures, which I already told you, which is a beam or stud based, or you can also have it as a periodic, which is repeated along x, y, and z directions, and pseudo periodic, which looks like a periodic, but there will be variation of unit cells, and conformal. Conformal means like there may be variation of the stud size, like functionally graded, or comes under this function. Conformal lattice structures. And these are the unit cells of ladinoid. It looks like this, and split pea will look like this. This is actually lattice structure, not a lattice unit cell. The particular one part is called as a lattice unit cell. This is neovious. This is a Sheward's diamond. This is a unit cell, and this is a lattice structure and gyroids. This all comes under TPMS. TPMS. What is a TPMS abbreviation? Anyone can unmute and can say maybe so that we will win in TPMS, which I told you in the previous slide. What is TPMS? Am I audible? Hello? Am I audible? Hello?
Yes, Madan, you are audible.
Yeah. What is TPMS? Any participant?
I think they are quite
Okay.
busy in their written exam, test exam. I think they will be preparing for it.
Okay. Fine. Cool. Actually, TPMS is a triply periodic minimal surfaces, which I showed in the previous slide. It's a surface-based lattice structures, and can also have this kind of lattice structures in the form FCC, BCC, or simple cubic structures like this. And there is a software called Topology where you can have this kind of lattice structures for academic research. You can um, work on and for your applications. So here, this is a TPMS, which is a gyroid or NUVS or Shivards in so we can create it. Or we can have this kind of beam-based lattice structures where you can have a unit cell with a sharp variation and there will possibly sharp corners. Or if we have this kind of honeycomb lattice structures, honeycomb path planning, people have seen the infill patterns which are edges of honeycomb structures. Same here, we can also have this kind of unit cells making the shape of honeycombs. We can have better energy absorption applications. And this plate is a 2D lattice structures. And so you can see this kind of periodic and non-periodic or pseudo-periodic. So non-periodic means there will be variation. The unit cells are very continuously along X, Y, and Z direction. And same, this is volume, which is having a material which is present inside the.
Hello, sir. Sorry to interfere. There are some questions coming in the chat box, sir. Do you want to
Okay.
answer in between or at the end of the session?
Yeah, anything is fine.
One question is like how to design hybrid type lattice structures.
Yeah, very good question. There are some software solutions that they can able to create this hybrid lattice structures. I will show you in the upcoming slides like what are the
Okay.
open
And
tools.
another question is any open source software for lattice structure optimization?
Okay. There is a
Okay.
software called MS Lattice Generator. And I have a presentation with
Okay.
some slides
Okay.
in this presentation. And
Okay. That
also,
is
yes,
okay. Thank you, sir. Thank you.
thank you so much.
And for
And
all the participants, one general announcement, the quiz link will be shared immediately after this talk. So please attend this talk. We will send you the link, okay? Because chat box is full of that questions. Yeah, thank you. Yes, sir, you can continue.
yeah, actually, I'm in presentation mode. I could not able to see the chat box here. I don't know. Yeah, it's there. Yes. Okay, fine. Maybe I can, if there is any questions, you can ask me as well. And because I've been working at the presentation, maybe if there is any question, you can ask me and then no problem. Okay. And we can have this kind of beam-based lattice structures where the lattice cells are kind of unit cell just replicated in the 2D, and we can also have this kind of lattice structures here. And TPMS structures, and for creating this hybrid lattice structure, I can suggest you to go with N topology because this is one of the easiest solution to create it. And apart from that, you can also create this hybrid lattice structures with some software solutions like CATIA 3D Experience. You can have Autodesk Fusion 360, or you can have this kind of Autodesk products like Hypermesh. We can have there is also one software product uh, which is Magix. We can able to create this kind of lattice structures, hybrid lattice structures as well. For hybrid lattice structure, I will suggest you to have two different STL files where you need to have two different lattice structure which you need to incorporate. Uh, Select first one STL file, then select a particular lattice that will be implemented. And for the second STL file, you select it and select the next lattice unit cell. Then you can have this hybrid lattice structures with the two different STL. Then you can combine the two STL files into a single STL file using software tools available in Magic. Yeah, and you can have this kind of plates or honeycomb lattice structures which mimics the shape of the honeycomb structures. And here you can see this stud-based lattice structures. This studs are repeated along X, Y, and Z action. And this also some of the other lattice structures like tetrahedral lattice structure and Kelvin cell. Or if we can have this diamond lattice structure, which mimics the atomic or the crystallography of the diamond structures, which like atoms are even present in the diamonds. The lattice structure also looks similar to that. And we can also, apart not only with respect to unit cell geometry, we can also have in terms of mechanical behavior. Now people are been studying the stretch, whether the lattice structures we can able to stretch it, or how much the flexibility is that, or how much the bending to absorb this energy load carrying applications. So far, such kind of applications also people have been creating or developing their own unit cells. You can also create your own unit cell using some softwares like CAD software tools like SolidWorks or Autodesk products. Then make it into a single unit cell. Then implement the import that unit cell in. I could suggest Magix as a STL file. Then with that same unit cell, you can replicate along X, Y, and Z direction. Then you can have your own unit cell with the lattice structures of your own, then there will be no possibility like what you can say the novelty in that creating lattice structures can able to get it, and you can do some applications like for applications like thermal or load carrying application, and you can compare with the standard size. People have tried like that only this kind of Kelvin cell or stress they found which is much effective compared to the PCC lattice structures. If you found some kind of lattice structures which is effective compared with the standard lattice structures which is available in the market, then you can also go for publication, or you can have talk to some industry. You can also make it into a large scale this lattice structures in their applications. And here you can have this kind of surface-based lattice structures. So here, this is as a actually surface-based, which is a surface element, and there are also volume. Here it is a solid. This is a sheet. Same guide. Here the surface, the lattice is having only the surface element, and there will be no material which is present inside the sheet. So it's a sheet which is covering like a STL file, which is a complete sheet. And there is nothing which is present inside. So we can have a for weight reduction applications or something. And here in this kind of solid, there will be material which is present inside this lattice structure. So that's why it is called as a TPMS. These are called as minimal surfaces, tri-ply periodic minimal surfaces. And saying you can see this unit cells of those lattice structures, which is from the standard software tools. Guy rods will be like this, and diamond will be like this, and IWP it's a name, and Fisher coach. So here there are, everything is having a difference. So why this particular lattice? The reason. So some of the things are it has no straight studs, excellent for bone tissue application and heat exchange. And why diamond is that it is for load bearing, as the name itself it is saying diamond, for more load bearing and higher stiffness. And primitive lattice structures are having more porosity. I didn't show you here, but it is having more porosity and better fluid transport applications like CFD. People have been work on to create this kind of lattice structures. Even now, people are doing a CFD analysis of the blood, like making the blood flow into the bones. We can also create a lattice structures, implement in the CFD, then create a mimic of the blood, and then use a CFD study in the bone. That also kind of such high skill. And Shiva's the more complex and provides also isotropic mechanical properties like isotropic means there were same mechanical properties on X, Y, and Z directions of the unit cell. And it can also have a kind of lattice structures which is inspired from biological structures. So here you can see this bamboo. This bamboo structures, it is a round shaped structures. So you can also create a lattice structures like Venn diagram. You can see the Venn diagram lattice structures, which is mimicking this bamboo And then the fish scales, the surface of the fish. You can inspire the lattice structure from that, and you can have this one. And then crocodile, the surface. Now, if you go and see the surface in depth in microscopy or something, you can have this kind of structures like it. So we can combine everything into one unit lattice structure, and then we can print it. You can do some compression test, whether it how much the load variation and everything, and you can also do some artificial intelligence, AI, like artificial neural network. You can implement and can predict the total energy absorption. You can predict the strength. You can predict the mechanical properties. Then you can do some mechanical characterization. Then you can have this kind of this is a complete one journal paperwork. Maybe if anyone wants to take up some research with a unique lattice structure, I would suggest you to study all the biological structures which you have been familiar with. And if you get inspired with some unit cells, then you can create your own lattice structure. Then do such kind of study mm, for creative applications in lattice structures. And there is also an application from honeycomb structure, which is a latticeal, which is already in the market. Plus, you can also combine some biological structures like this is actually a tortoise surface. If you see the what you can say this shell, the tortoise shell, body shell, it has a structure because tortoise shell is very hard. So people have studied how the shell is very hard, whether it is completely solid. No, there is a lattice cell is replicating in their body. So it is a shape like this. Then combine, which is in the honeycomb structure, which is available in the market, with the tortoise inspired lattice. Then we can create a lattice structures, unique lattice structures like that. Then we can able to study for energy absorption. People have worked on with this energy absorption for especially impact energy. And they printed this lattice structures of honeycombs, and then this dual inspired, bio inspired lattice structures. Then they found whatever this honeycomb structures, new honeycomb structures are much better than the commercially available in the honeycomb structures available in the market. This was published recently in 2025. You can also check the journals. And related to the people who asked about the software solutions, especially whatever they told, applications, advantages, types, everything is a concept. But as a researcher or as industry, how we can able to take it and make some physical product, we need to have some design, right? So for creating the design, these are some of the software solutions which is available. We can have this kind of MS lattice generator, which is this one MS lattice generator, which is open source. This is open source, and here this material magics, which is commercial, and in topology, and then latticeworks. This is actually a program-based lattice sector. This is actually a MATLAB program is there, which is actually also open source. I will show you the upcoming slide. So this is actually a software product, but this is actually a code. You can also create your own codes, then you can make your own lattice structures, and you can also edit the codes and implement in whatever the STL files which you have with the help of this lattice works. And this MS lattice generator, you can't able to implement your own lattice units. There are some predefined lattice units which is available, and some standard shapes. Only we can able to create this kind of lattice structures. And this topology and material magics, people have been using it more to study this lattice. If you take publications which you have published with the help of lattice structures and metamaterials over the last 10 years, you can see a lot of topology software tools people have been working on to create the lattice structures. And I told you this MS lattice software. You can also download from this GitHub link, or if you type MS lattice software download, You can get a link in Chrome and can download this exe file. Then click next, next, next. You can get a window like that where you can create your lattice structures. Here there is an option for uniform TPMS, or you can have this functional TPMS, which is a functionally created TPMS structures. And then with the help of implicit function, with the help of your own equation, you can also create your lattice structures in that. I have the software here in my system. I will show you the demo. So here you can see the functional TPMS. You can have this variation of this TPMS structures. Like here you can see the lattice cell is thin, but you have more solid element. So this variation of gradients you can able to implement with the help of this MS lattice generator. Or you can have this kind of equation, implicit function. You can have this equation like sine theta, cos theta, which you've been using it for creating curves. If you can multiply those sine thetas and values of those curves, then you can have this kind of structures, which you can able to visualize those structures with the help of this software called MS Lattice. And I'll show you the software, then I'll go to the next software tool. So here you can have this, you can see this MS Lattice software in my system. So here, if you have, I'll reload it. And it's not open. Yeah. So it's open. So it will take time, some time to initialize, and the software will pop up. A window will pop up like this. Yeah. Actually, it's a MATLAB based program which is running in the background, but you don't need to implement MATLAB. Okay? There is a MATLAB runtime software tool which is default in the software that will be that will install in addition to your MS Lattice software is being installed there. So once it get initialized, you can have lattice structure which have been created here. So here you can see this lattice unit cell. So if you want to vary the size of the unit cell, then you can plot it as a surface, or you can plot it as a lattice. Surface means it has a surface. You can see it is a surface. We can't able to print it, and we can't able to export it as an STL file. Once you pick it as a lattice, if you click plot, you can create an STL file. Then you can also export it here and take it to this, and then you can also export it from this software. Okay. So here we can have this kind of cylindrical structures. Okay. So we can have create a structure. So maybe you can also try with this software tool. Maybe it is taking some time because multiple things are running my system, so it is taking some time. You can also have this kind of um, spherical lattice structures, and then you can have this functionally graded lattice structures. You can see you can also vary structures, and you can see. Different lattice structures for diamond. And then you can also have this kind of implicit function. If you vary this instead of sine 2, you can have sine 4. Then you can plot it. The structures will vary. Okay. So you can also have this kind of things for hybrid lattice structures and for implicit functions or for uniform lattice structures for shapes like a cuboid, elliptical, or spherical. So this is the open source thing where anyone can work on this kind of sub lattice structure generation. And there is also a software tool called Magix, where you can able to create lattice structures. There are some tools where you can also add your own lattice structures. This is a unit cell, and you can see cube with the unit cell which is repeated along x, y, and z direction. If you want, I can show you the magics. So this magics you need to purchase license, then only you can able to use it. It is not a free software solution. Um, so once the magic opens, yeah. And here also you can have your own STL file and own STL, own unit cell, everything. There is a possibility. If you create a if you have this box, you can also create or some cone. If you want to create a cone, you can have some standard shapes. Then you can implement the lattice. Go to structures. Then we can have select no outer shell. Then click next. You can have an option to select what are the unit cell. You can see what are the unit cells is available here. Or you can also add it and you can add your own unit cell lattice over there. So MSG, I can have this my unit cell lattice over here. Or what are the available here. So you can have create, can add, you can have your own lattice structures over there. So I'm selecting this one here, click next. So this is actually one unit cell. I want to make it as a small, then no outer shell, click next. Then I'll reduce the size to 2. And it will take some time to generate it. Then you can create have your own lattice structure. Okay. Okay, this is actually how a 3-dimensional lattice structure looks like. And this is actually the cone. Okay. Okay, just close this. That's how we can able to create your own lattice structures with the help of this software called Mimic and Magix. And there is also a software solution called Topology. I don't have in my system, but I have previously worked. This you can see a kind of cubes where you can create a lattice structures in the form of arrays. Like this has a unit cell of different size and the same unit cell is same, but it has the stacked thickness is very along x, y, and z direction. And then you can also have some lattice structures with different geometries. Then you can study the impact and you can identify which is better for the requirement which you need. For such application, this kind of design of experiments people have been working on. by varying the process parameters and the levels. So such kind of things we can able to do it with help of this and create a plate with a number of cells instead of having creating a separate one by one. You can create it together in this, and you can also study for applications related to additive manufacturing. You can also do some simulation in this software. Yeah. And I told you this software called Lattice works, where you can also, this is actually a MATLAB based software solution. You need to have a MATLAB to use this. This was published in 2025 in the recent MATLAB toolbox for non-uniform gradient multi-morphology lattice structure generation. So here you can see the linear gradient. So here the material is varying along x, y, and z direction. Or can have this kind of a TPMS structures, or these are some of the capabilities of this lattice works which we have posed. And this is actually a spinal implant. The spinal implant they optimized using this topology optimization tool. Then you can also implement the lattice according to the load bearing applications. And this is an interesting application for thermal, according to the twisted cylinder thermal gradient. You can also implement the lattice structures accordingly. So apart from that, we also done some work.
Excuse me, sir. Would you like to answer some questions, sir? There are some questions in the chat box.
Yes.
I will read it to you, sir. I will read out. Out of the different software packages available for lattice structures, which one is used for topology optimization?
Topology optimization, lattice works is much better because we can have MATLAB tool, which I already just now I showed you in the previous slide. Because this one people have worked on with for over for last 10 years, people are using this beam for topology optimization because there is a MATLAB topology optimization toolbox where you can create the topology optimization geometries. So then you can incorporate a lattice structure using this software code available in the software MATLAB toolbox lattice works. Or else you can also use this kind of software called NTOP, where you can topology optimize using this tool called optimization. Then you can incorporate a lattice structures according to your requirement. These two are much better.
Sir, one more question from that same Dharmadure. How does topology optimization influence lattice density and unit cell distribution in the software?
Yeah, and this is also another interesting question. The thing you need to study according to your application, I could suggest, because we could not say by visualization how this unit cell will impact my requirement. You need to create your own lattice structure. You need to incorporate in your design. Then you need to do some thermal analysis. Sometimes if you do simulation, it may be much better. But if you print it, there will be additive manufacturing constraints like distortion or thermal gradient effect also. I would suggest you create your lattice structure, print it, study some physical things. Then you can have some trade-off with topology optimization and what are the applications which you will require. Yeah.
One more question is there. Actually, I'm not clear about it. Is this any software available for all 3D printing design or it is manufacturing specific?
3D printing design, like I hope the person is asking related to the DFAM tools. I hope so. Currently, I hope 3D printing software tools like generative design, topology optimization is now a part of whatever the commercial softwares in the market as of now. Whatever the companies like SolidWorks or Autodesk, like SolidWorks is a Dassault Systems, Dassault Systems or Autodesk, or if you take any Creo, which is ETC. So all the software companies, are moving into this additive manufacturing because they are finding this software tools like generative design or the topology optimization are the future for their company's growth, because many people are now moving from conventional subtractive manufacturing to additive manufacturing for uh, not only for their printing easier. We cannot there may be a possibility to make no need to make dies and tools for a smaller batch production. And this kind of software tools are also provide opportunities to implement complex geometries like topology optimized geometries or lattice structures in their design. So there are tools, all the software tools, commercial software tools like design softwares are using this deform tools one by one, implementing there into that. I would suggest you check with the recent version of the software, and if that is suitable for your requirement, then you can go for purchasing and use it, or you can explore
Okay.
open source.
Thank you, sir. Thank you very much. You can carry on, sir.
Thank you so much. And here we can have a paper which is published recently. We are presented at the ASME conference. I happened at IIT. It was hosted by IIT Hyderabad. It happened at Hyderabad in September. We have created a cranial implant, polymer implant, the porous structures. We 3D printed using material extrusion machine, and some of the results of the paper are I'll show in the slides. So here you can see a cranial scaffolds. It's a patient specific cranial scaffolds. Here is a skull. It's a broken skull, and this kind of cranial deaths are happening all over the world. Like almost you won't imagine, more than 10,000 deaths are happening every year with cranial head injuries, a lot of accidents, a lot of mm, uh, problems related. Like so we tried with polymer scaffolds because there is a material called PLA, but there is some question, or there is or we need still working on to identify the longevity of the implants, because commercially available implants like are made of materials like titanium or stainless steel. And so there are also people who have been working at the PMMA, polymethyl methacrylate implants. These polymer implants are alternative to the metal implants, which is affordable and good compatibility. And osseointegration effect, we have studied in this particular research, and we have provided some outcomes in the paper which we have published recently. So first we designed our scaffolds using this MS lattice generator, which I told in the previous slides. Then we converted this file into a 3D printable sections, and we printed the scaffolds using this material called PLA. And we studied the cell culture in vitro mode, and we studied this extracellular matrix like a proteins absorption in that plants we studied. Then we also conducted some blood viability assays with a real human blood. Then we did some assessment in that. We have presented for application for humans we proposed in that. So here you can see this cranial implant model, which have been printed with TPMS lattice structures like gyroid, UVS, diamond. This is actually the structure which is generated by MS lattice, and this is the unit cell which we have printed. So once we printed, we have studied the variation with respect to the unit cell size, varying the unit cell size and varying the unit cell design with the 3 different designs. We printed some structures. Okay. Then we conducted this in vitro analysis for calcium carbonate and dimethyl fluid. These implants have been dipped into that solution. This is a procedure to make the solution, and we conducted for a period of time, which I'll show you in the coming slides. And there are protein absorption studies in those implants. And then here you can see we studied protein absorption. We found this neovious structures good protein absorption compared to gyroid and diamond implants, and that was a outcome from this protein absorption studies. And we also studied with simulated body fluids. This is the gyroid, neovious, and diamond. That's how we created the simulated body fluids with the composition of various chemical elements. And from that result, we come to some conclusion, like how we have done this hemolysis studies. Is normal saline water is mixed with fresh blood, and then is actually a healthy individual how blood body fluid would be. And it was coated with the calcium carbonate, and we had to bring it. And the capability of scaffolds have been analyzed to prevent the damage to the red blood cells, which results in the rupture of this red blood cells. So this is how we calculated the hemolysis ratio. So here we have a negative value and positive value, and what are the values which are calculated from the sample? We calculate up here, and then calculate this hemolysis ratio, hemolysis rate percentage. So here we found a structure called neovious. Lower the value, which is better. So we found neovious is much better, and protein absorption also neovious is better. And so that was the result from this hemolysis. And hemolysis is when red blood cells break out or are destroyed. You know what is hemolysis, right? It causes hemoglobin, and the other cells is split in the bloodstream. So we come to a conclusion it will hemolysis rate based on the rate percentage that a neovious structure is much better compared to the other structures. And then we did some study for 12 days and 24 days. These are some of the results with respect to the sample weight. And we also done some structure, you can say the mechanical analysis. We found neovious is almost doing, it's not good as like gyroids, but neovious is in between this gyroid and diamond structures. So with respect to biocompatibility, neovious is doing much better, but with respect to mechanical things, it is in between the two. And we had done some tensile test in that lattice structures we have printed. From that, we found this neovious is doing much better compared to diamond or gyroid structures. So that when we come to a conclusion, as neovious structures are much better compared to gyroids and diamonds in terms of mechanical as well as biocompatibility studies. So then we improve, because we need to have that not only biocompatibility, we need to have some load which is acting there. That's why we did both. Then we designed the implant with the scaffolds. Then this is the implant which we fabricated with the help of neovious structures. So the conclusion is it assists in tissue regeneration, and it also paves way for affordability, because we have printed with the PLA material, which is quite affordable. But there may be a possibility or the study which we need to take it for, because we did it for 12 days or 24 days. Some implants have some critical surgeries where the implant need to be in there for almost years for scaffolds which need to grow for completely replacing of skull where there is no presence of bone. If there is a partial presence of bone, this kind of application will be useful. If there is a complete replacement of the bone in that particular skull with the help of a scaffolds, I would suggest you to go with metal implants like a titanium, which is costly. Or if you want to go with some cost-effective options in the metal additive manufacturing, I suggest you to go with stainless steel implants. And we have also done a paper with the functionally graded lattice structures for femoral processes, which is a hip implant. So, so here, the hip anatomy. As you know, most of the audience are from biological or medical background. So, the hip region, which is a femoral bone. And people are using these implants over a period of time or due to some injuries. People are using these implants to replace the bone which is present there. There we can also use customized implants based on the patient-specific geometries. The only option to make those implants affordable is through additive manufacturing because we can't able to make dies and molds and make those implants, right? So here additive manufacturing, there is a possibility to for weight reduction or for better ocean integration, we can implement the lattice structures into it. So here we also tried with load bearing application. We studied the load bearing, and we designed some lattice structures. And then we studied the possibility of which implant material, sorry, which implant lattice unit cell is better for those applications. So here, this is a TPMS. You can see type A periodic minimal surfaces, which is varying along X, Y, and Z direction. This functionally graded lattice structures are much better compared to the standard unit lattice structures. So these are some of the background which people have worked on with that lattice structures. Why we went for that is that multi-material tends to be failure at some cases because if we have two different materials and yeah, sorry, I got muted. So this may be abrupt failure at the process and cement interface zone, and we can also in this particular study, which people have worked on with this femoral process using FE analysis, then possibility of weight of the femoral process may be reduced. These are some of the remarks. There's some mute. Okay, fine. Please, participants, can you mute yourself? And thanks for the cooperation for this much amount of time. I hope I won't bore yourself. This is the final, and I'll try to conclude as soon as possible. I know you have been in the presentation for the last 3-4 hours. I hope so. Yeah. And then the Ravichandra, he studied 5 different lattice structures and they found these TPMS structures are much better compared to the previous solid stud-based lattice structures. So here we can have this functionally graded lattice structures using this diamond, gyro, primitive, which is commercially available in software tools. So that's how we come to a conclusion to use this kind of structures. We tried with functional graded using the standard unit cell which is available in commercial software. So here lattice structure modeling. So how we did to calculate the porosity or porosity percentage is that if we have a unit cell in the standard shape, and this is a lattice structure with BCC. So this is a volume of a part within corporate lattice structure. This has a lesser volume. This is a more volume. So volume of, say, this is 9 and this is 10. So 9 by 10 is 90%. This has a porosity. Something like that we can calculate it with the help of this formula which is given here. So here you can see the volume of the material and the porosity percentage and cross has more porosity percentage. And, yeah, and you can see this kind of 4 different lattice structures that we implemented functionally graded lattice structures and as a cube which we have printed initially for compression testing. Then we implemented in the femoral process which we have developed. So these are the femoral processes without the cap. So 4 different lattice unit cell, which is functionally graded lattice structures, and then with the cap here also functionally graded lattice structures, more porosity here and less porosity here. So here you can see this functionally graded lattice structures which are designed. It's a commercially available software tools, and we did some load analysis in that using a software called ANSYS workbench. Then we found a factor safety of 3 which we can implemented, and come to the conclusion that BCC is providing performance much better. Then we printed that lattice structures with because it has very high intricate geometries. There are some tools or the machines which can print those geometries. So we have also have one printer which is a Stratasys J5 dentajet printer in Satyabama. There I have printed this complex unit cells with the help of the design which I developed. Then we studied from the analysis, and we found that this BCC is providing much better. And also we studied how much amount of load which is acting over there. 22 to 35 megapascal is required, but if you print it the same thing which metal, it will go up to 316 megapascal. So maybe we can able to achieve factor safety with 2 or 3 sufficient. Then this kind of lattice structures are good to for wave reduction as well as osseointegration application. So that was the outcome which I presented at that conference, and it got the paper also published in chapter and Springer. So, and I will suggest you to go with some possible researcher, as academic researcher and industry people who want to work on or create. Is that there are people who have been working on creating a database, process, structure, property, behavior analysis with respect to process, like which kind of additive manufacturing process you are using, and what kind of lattice you are generating, and what is a mechanical property or a biomedical property which you have been creating. From that out or the outcome from the research, you can have create a database. So, and then AI enabled lattice structure generation. That is also an inspiration from natural structures or living organisms. Then optimization of process parameters from the printed lattice structures. Then you can also incorporate advanced machine learning algorithm to predict the material properties instead of going with all physical things. You can also predict something with machine learning algorithms. Then you can also identify some possible applications with the lattice designs. And here, as most of the audience are from India, India is eighth active country in AM research, but we are #1 population. You can also think of some advanced countries like Germany, US, China, France, Italy, UK, Japan are much ahead in additive manufacturing research. So these are some of the esteemed organizations in India have been working on additive manufacturing for almost decades. And this is a generative design concept in one innovative application which I want to share with you, because with the concepts we have studied, we need to find some application. This is one interesting application which was found by a company called MX3D at Netherlands. So they found this structure which is present in the 6-axis robot. It's a pick and place robot. So for weight reduction and better stiffness, they took that particular design. They incorporated a generated design into that, then 3D printed it. After that, they implemented for the particular application, and it was supplied by ABB. You may know. Yeah. So that's for more information or queries, you can contact me to my through this mail ID. If you have any questions, you can unmute us and ask, or you can put it in the chat box. Thank you for your time. I hope I'm correctly ended up with the time.